ASK Online Academy webinar on the topic Optimize cores and molds digitally with best-in-class core making simulation ArenaFlow. My name is Benny Daniels and I will guide you through today's webinar. I have the pleasure to introduce to you today's speaker, Mr. Thomas Brand. He's a member in our design service in the US, but he started out working for what was to become the largest and most modern pattern shop in Scandinavia with global customers and also with a good connection to DISA. After 17 more years, he started a new position in 2007, working for the Ashland Casting Solutions with various simulation softwares and 3D modeling. In 2010, he had been offered a transfer to Ashland, Dublin, Ohio campus, and has been working for Ashland or the ASK Design Services US ever since. Thomas is married more than 30 years with 2 daughters and a son, and he's now living in the US while either working or attending colleges and universities. He was nationally ranked competitive car player in Denmark for many years and on the talent list for competitive rowing until an injury, unfortunately, but still enjoys being outdoors on the water and whenever possible, mostly during the holidays in Denmark. But before we begin the webinar, we have a few organizational notes for you. For data protection reasons, no clear names are visible. The image and the camera transmission is also deactivated. You can submit your questions via the chat function box at the bottom right. We will, of course, try to answer them afterwards, as many as possible. Questions that we are unable to answer in the webinar will be addressed by our experts afterwards. A recording will be made available after the webinar. And so now I hand over the floor to you, Thomas, and have a good one.
Thank you, Benny, for the kind words, and I will continue with the presentation on ArenaFlow. First of all, what is ArenaFlow? ArenaFlow, as it says, is a virtual core machine. As inputs, we take your process information, send data, and apply those in a virtual world. Like the example on the screen, see particles as they're being carried into the cavity and compacts, orange being at the highest level of compaction. This example shows geometry, critical surfaces, blowtorch positions, sand particles, venting modeled as discrete boundaries, no need for 3D modeling of vents, sand entering and filling the cavity, look for last 2 areas to fill, slow filling, alternative visualization, again, particles entering, compacting, sand speed, combining 2 results, and potential defects related to the filling pattern. So the fundamentals of the software is basically modeling particles as solids and air as continuous media exactly as it would happen in a core box. See flow vectors representing air, how they slow down as particles build up on vents. For core blowing, we have 3 possible scenarios that we can model. Cold box, traditional binder coated sand, shell, warm box, hotbox, and lately the addition of the inorganic process. Images show an example of validation done prior, almost 20 years ago. These images were created, comparing simulation to an actual tool with a plexiglass plate, so we could high-speed record and make sure everything aligned. Additionally, modeling is a gas curing. See how the gas front makes its way through the core, and again, simulation compared to reality. In addition to the traditional airflow model, we have added dehydration, so now we color the full spectrum of curing. In addition to that, we have the ability to model the full setup, sand moving through magazine into the cavity, looking at how material is distributed through the system. Any potential problems like blow tubes running out of sand or not ideal positioning of cavities. So what can we do? How can we add value? In the core shop, we can look at improving core quality, reducing core-related casting scrap, improve productivity by tools running cleaner, more efficient, optimizing blow cycles. Thus, by increased core quality, reduce the need of any repair or handling before the core moves into the casting. We can look at what happens if we change the grain fineness. Take a look at optimizing gassing cycles and save time by applying any possible trial and error in the virtual world before we actually implement them in the tool. Is it worth spending the time on sending the tool out, getting it fixed, put back in production? As this is a costly process, there's a lot of value of doing this in a virtual world prior to implementing changes. Pre-production, design the tool. So again, minimizing trial and error. Make a shorten lead times. Look at material again, process conditions. Get to know what to expect. And finally, exceed expectations. Take a look at the various outputs. In this case, we are comparing bulk density and fill time. You can see a direct relation between the last to fill areas and soft spots being the dark blue. They are of lower density, and as they are away from the blow tubes, these are critical and likely to create a defect. Turning the tool transparent, looking at particles as they fill the cavity. Particle volume fraction, so sand to air ratio, again in the cavity, various time steps. Orange being compacted sand, blue being loosely compacted and still moving. Again, it's clear to see that the areas between the blow tubes in the right side image are filling slowly and could be potential problem areas. Sand speed. With this result, take a look at how fast the sand moves. Sand moving at a speed of less than 2.2 meters per second will not compact further. Airflow. Looking for uniform airflow. Is there any turbulence? How balanced is the airflow? Air pressure. Initially, you want to see the gradients being as close as possible, as this indicates a fast exhaust, fast pressure drop, giving you good airspeed. And as we know, without air, we are not moving any sand. Blow tubes. We can track the sand as it enters the cavity from which blow tube it enters, looking at how fronts stitch together. We do not want any sharp fronts that could indicate a problem, stress crack, weak spot. We want the sand to knit nicely together. Gives an idea on how uniform the core feels. Geometry dependent, but still gives you a good idea. Tool wear. Get an idea of where you might see tool wear and potential resin buildup in the tool. We've got a sample of curing, steady state, fairly fast calibration, gives you a image, an idea of where if you see any stagnant air, which could cause problem for either blow or curing. Transient curing, see the air gas as it moves through the cavity, with the gray areas being cured and the orange area not having air contact. If you see any early protrusion on the drag, that indicates possible bypass. Another example of transient curing, see the cured areas as dark gray and uncured being sand colored. So what's new? Like before, we added the dehydration module. So let's take a closer look at that. Setup, again, we take the process and apply it in a virtual world. Setup example, show phases applied for heat and phase where we have our purge air inlet. Sand temperature assumed to be at room temperature initially. Right side, boundary conditions applied, vents and ejectors colored by size. Right, left side, Same thing, boundary conditions applied and colored. As the tool heats up, it's likely that it could open up along the parting line. So we applied exhaust around the parting line, various degrees of opening. Importantly, now we take a look at the moisture content. What's transparent is anything that has 10% moisture. The volumes are areas that has a higher percent of moisture. So you can track the formation of the shell, look at when the shell would be thick enough to eject and handle the core. It's possible to adjust the residual moisture limit in the setup. A couple of other outputs: air temperature and sand temperature. Water in the air as it's being transported, and air exhausts the cavity. Take an example as probably the best new addition is that we've changed to TechPlot, which is industry standard for post-processing of fluid dynamic results and particle flow results. As it says, a license of TechPlot is now included in ArenaFlow at no extra cost. So then in this video, we'll run through a series of examples, initially a single cavity, looking at particle volume fraction as you step through time, modifying the view, stepping through time, applying value boundaries. So now we're only looking at the areas of low compaction, manipulating the view, stepping through time again. So it's to track these last to fill areas. Looking at 4 different results, same core, making it easy to compare results. And then they are synchronized. So zoom in, move, rotate. It's all simultaneously. And step through time again. Replace one result. So in this case, we replaced the pressure result with the colored sand. And instead of views being synchronized, now we just manipulate the color sand view while the other views remain in the original orientation. And stepping through time, particle speed is limited, so anything below 0.2 meters per second has been removed. Comparing two versions, obviously version number 1 did not show a filled cavity, so we had to take some measures, make some adjustments, see if we could come up with a design that gave you a good and robust filling. So again, now all 6 views are synchronized. Let's see how different the two versions are with regards to fill time. The shorter the robust, the shorter the fill time, the more robust your process is. Another way is to look at the volume, compare the volume between the two versions that enters cavity. Easily graph out volume. Lastly, but not least, we can compare the layouts, cope and drag view. So we can see, in addition to adding blow tubes and creating exhaust all across the bottom of the V, we ended up with pretty good design. Another thing is cloud licensing, now making it possible to easy access, easy manage a license. Makes it easy for us to provide you with a license. You do not necessarily need to have your own in-house server. It's certainly an option, but you can run a cloud license. You cannot run the software itself in a cloud. That would have to be run locally. But the licensing is now possible to share via the cloud. So as a conclusion, I hope this brief overview has given you an idea about how ArenaFlow could be applied at your facility and add more value to your company. So we covered the addition of the dehydration module, TechPlot, cloud-based licensing, all additions made to improve the usability of ArenaFlow. And with that, I would like to turn you back over to Benny for questions.
Okay, thank you, Thomas, for this very interesting presentation and the information given with it. I can see in the chat box that there are some questions. Let me check out, how long does a typical simulation take to run on the computer?
That is a great question. Because we do particle tracking, it is not necessarily a fast calculation. So geometry dependent and particle cloud dependent, a typical simulation takes anywhere between 24 to 48 hours to complete.
Okay, that's pretty cool. There's another question. Can I have core parts simulated without purchasing a license of ArenaFlow? Is that possible?
Another great question. And the answer is yes. We offer this as a simulation services. So you can reach out to an ASK representative, the account manager that visits your facility, and we will be glad to quote a simulation using ArenaFlow.
All right. So, what else do we have? Who do I contact to discuss ArenaFlow license topics or projects or anything connected to ArenaFlow?
I would recommend, like I mentioned before, reaching out to the ASK account manager that visits your facility, and he or she will get you in contact with our design services who manages ArenaFlow software.
All right. There's another very nice question. How many cores does the multi-core solver support in ArenaFlow?
That is a great question. We do not restrict the number of cores. So a license of ArenaFlow will use X numbers of cores on a single CPU. There's no, we do not support clusters, but any one CPU with X number of cores is supported by one license, and the software will use all but one, which is kept free for like trivial uses like mail, office, whatever. So all cores minus one is included in the license.
Okay. Well, one question from my side. What's the kind of format that you need if you want to run a simulation? Are there different kind of 3D modeling preparations needed by pattern shops or by the single customers, by the single foundries?
That is a very good question. ArenaFlow itself, as an input, requires STL files. It does not read anything else but STL files. The models we require are the internal surfaces that has contact with sand. So it means the internal shape of the blow tube. We need the core, not the core box. Same thing with magazine, internal shapes that has contact with sand. And we do have a project information sheet that we always send out and share with people prior to running a project.
Okay, so as many boxes filled in that questionnaire is helpful, right?
Correct.
Okay, and there's another one. Is there a default installed library of sand materials in the software? In that case, are there any experimental characterized sand mixtures also available in the library?
Yes, there are default materials. However, and that cannot be stressed enough, because of the particle distribution, etc., is critical for simulation. We always ask that you use current data and data that are resembling what you're running in your facility for this particular job. But yes, there are defaults which can be used as a skeleton when building your correct data set.
And another question that came up to my mind is, can I also create different kind of materials, like mold materials or something, to add that also to the library?
Absolutely, it's possible. You can always create your own standard database of materials you want to apply. The thing you would need to know is the percent retained and mesh size and the material density, not bulk density. And when you have that information, you can build and apply a data set for any given material that you would use in a core production.
Okay. So I see that there is no further questions in the audience. So yeah, there's nothing popping in. So I think if there are no further questions, I simply, before closing the webinar, I want you to remind also to check out our homepage in the internet. You can find all different kind of supportive kind of informations there, like product finders. You can also reach out on white papers or technical papers available there, also for download. Or you can address also your detailed questions within the ASK, the expert questionnaire. Simply type it in and you get a response as quick as possible. And of course, there are more webinars to come within the ASK Online Academy, as well as the recordings of the past webinars. So if there are no more questions popping up, I see there's only one thumb up at the moment. We wish you all a very nice day or a very good evening, wherever you logged in, and looking forward to your evaluation of the webinar directly after this one. And one more time, thank you, Thomas. Thank you all for joining and attending today's webinar. Take care, and I hope to see you maybe next year on GIFA 2023 in Düsseldorf. So have a good one.